Okay, so I want to look at photons again. Let's call this photons 2. Okay, because I think it's really, really important that if we just say fluid space and then everything else comes from that, like in the four forces, okay, suddenly we have a flow this direction through a wire or through, let's say, a plasma, right? Current might travel down a plasma. Okay, as it goes like this, low pressure, field moves in, innate chirality because of our temporal thing, that we are on a membrane of the present, therefore chiralities and all of that. I don't know where I addressed that. I'm pretty sure in one of my other videos, topology, but today photons. Okay, so let's make this. This is the proton there. There's a proton there. Okay, and scale is obviously not going to be accurate. This is an illustration. Okay, and our model posits that this is an outflow. Right, gravity points that direction, and the compression of space in that area creates positive charge. Positive charge is convergence in one dimension, and gravity is convergence in a different dimension. One is density, one is actually flow. So to compensate for this outflow, this loss of volume here, what we have, and we'll do a simple one, is an electron here, which is actually the eversion of the proton. Circle of inversion applies all throughout physics. The proton is the inversion of the electron. The electron field is the eversion of the proton. So what we have here is the electron, which supplies an outflow and I'm doing these little loops because let's say there is a particle outflow, though I don't think it's actually the case. It's just an outflow. You don't need a particle to make an outflow. An outflow could happen along a plane, it could happen along a line, it could happen in any shape you want, or in theory sort of, but it doesn't usually. But this is very simple. Electron is 3 axes of actually what's called inflow, because the fluid is coming into our dimension. Flows into our space and out in the middle. Okay, so now we have this is a low pressure zone, effectively. Right, because stuff is going from here, this direction, getting compacted here, which means it's getting stretched out here. So here's a low pressure chamber. Surrounding an atom, and I'm going to erase a bunch of stuff. And beyond this, we consider an atom to be neutral in that the charges balance. So exactly, an electron is exactly enough inflow to compensate for the outflow of the proton. Okay, so now we have a resonant chamber of one electron, and this proton has a outflow at a certain rate, so therefore the electron is going to be exactly the same, compensatory, right? If you have more pieces in here, especially more protons, because they are outflows. This is why neutrons don't contribute to electric charge, because neutrons are nothing. They don't need to be compensated for. Okay, but this gets, okay, wait. So a photon now comes in. Or let's just excite this. Let's say this is S1. Okay? Sorry, you know these are improv. S1. Okay, and then we somehow, this atom gets excited from a photon coming in, but we'll deal with that later because incoming is more complicated than outgoing. S2. Okay, so this is S2, this is S1. This electron got excited up to this state, but now it's at its limit and it's tired and it wants to collapse back down into a lower energy, which is actually higher energy density form. Okay, so it goes from here to here. Right, this is the drop in orbital. Right, this is a well-known thing, right? So what happens? Wait, there's space all around here. So suddenly there's a low pressure, like this has disappeared. So this now all has to move in to compensate, which then creates a low pressure zone here. And what we have is a low pressure spherical propagation in all directions. This is the entirety of the probabilistic sphere of the photon in quantum mechanics. What we need to do is, if we just substitute low pressure for negative charge, higher pressure for positive charge, it doesn't matter the direction of that, both contribute, or then some contributes to gravity as it's how much it impinges on the space-time continuum. But of course you have to have an orbiting photon. But see, okay, so there's photon. This compressed, the electron fell in. Suddenly space has to fill this gap. So space rushes in, which creates this spherical shockwave moving out. Okay. So let's, I don't have a good eraser right now. Boop, boop. So let's take it the other way. Okay, so that's how you make a photon. It's from the implosion of an electron orbit. Okay. So now let's absorb a photon. Okay, and the reason there's various reasons there's quanta, but I mean the localization of the photon happens at the point of reception. The photon is a big sphere. Where you burst that bubble, where you absorb it, is your detection point. But that is, I believe in Bohmian mechanics, and there's like a whole layer of shit going on, pardon my French, that modulates this and determines which piece of metal is going to be the one where that photon ends up. And I think it's bizarre to expect otherwise. Okay, so here we go. So here's where the we have an electron in S1 orbit. Okay, and in comes a photon. Now this photon would have been the photon that was emitted only from, see, this is a S2 to S1 collapse. There we go. Okay, so this wavelength. So in comes this, because this is actually, the absorption wavelengths are the absorption wavelengths, and they're harmonics of each other because, you know, if I started singing here and I sang on an E, the piano in the living room is going to start ringing on E. And all the harmonics, therefore, E, E, B, E sharp thing, you know, doubling up. It's very simple. Very beautiful mathematics. So in comes a photon, which is also, right, one of these spheres where this distance, the wavelength, the time interval of it, is going to fit exactly here. And therefore, when it hits, it sits perfectly in there, adds to this volume, expands this shell now out, because now it's got actually like sort of double the volume, because it sort of has an extra electron in it, right? Because that will collapse, become a photon. Why is a photon not just negative charge or just positive charge? Okay, because photon is a bilayer. This, the external edge of the photon, is divergent at all times. It's radially coming out. This is wider than this point on this side. Doesn't matter the wavelength. One side is always going to be, this is the divergent side, this is a convergent side. Divergent side, convergent side. Okay, and this is why there's an electron, which is the initial wave, and then there's the positron component, which is space filling up behind the bubble of the pressure. Where it comes in, it's simply, this is a resonant chamber. It fits into the resonant chamber perfectly because it's the same frequencies, give or take. And I thought about that. It's kind of a funny thing, right? If you have some hydrogen here, whatever, you have a red light, a super blue light here, a UV light here, and you want to cause a chemical reaction that doesn't require UV light, it requires a lower frequency of light, right? Can you just shine your UV at a really, really far away object and you wait for space to bend the wavelength till it matches the reception site? Weird trick, right? Just a side to side. But this fluidic model, just all we need to do is take the existing quantum mechanical math, reapply it so that it's applied to a fully fluidic space. Okay, and then what we need to do is remember to apply regarding the energy density of a location. As the energy density goes up, the metric itself gets smaller. That is gravity, it's the metric. Energy does impinge on space-time, but I mean, let's face it, like, until you get up to crazy high X-rays with phenomenally short wavelengths, but therefore all the Plancks in the energy dimension rather than the time dimension, until you get up to those extremely, extremely high energies, the amount that the energy impinges on gravity is minimal. I mean, it's c squared. Come on, look at that. The c squared part, which we'll get to in another video, I mean, the energy density required to create mass is extreme. But how do you get that? By putting it in orbit so that it's always in the same location. The energy is confined. This is how you create mass. If the energy is propagating, then this is what we're talking about. This is the wavelength. Is this. Is the membrane thickness for a photon. Just take quantum mechanics, apply this, which is negligible in most cases anyways, right? But it is there, and we could just apply it at c squared. There's like, I don't see that the math for it is actually all that complicated. Limit, highest limit of energy is going to be a photon of 2 pi Planck length, wavelength, 2 pi Planck length, because that is the surface of a Planck, and therefore you get trapped over yourself and you become a piece of mass. Okay, this makes a 90-degree. When you have this energy density, you make your refraction index is 90 degrees, and therefore you end up in the rotation. This is ridiculously high energy. We're only getting there with some of our most potent lasers recently, and this is exactly what they find. It's like what happens is you blast it, and you sort of like you literally create a hole in space, because once you've reached this, you might fall apart and become an electron and a positron. And B, if you got up into the highest levels, then what you become is the vacuum energy. And then all space will crush around that. You know, tiniest black holes have the field strength is sort of like the most compressed, because there's less surface area to apply that hole. Okay, messy. But volumetric application of the electron shell becomes the entire probability sphere in quantum mechanics, but let's pretend that instead that probability sphere is an actual sphere of low pressure. Now entanglement is not a deal, because this is basically sort of like a superfluid, so you interact with this part of the membrane over here, but the membrane is a singular process. So you interact with here, it modifies over there. Oh, yeah, let's do this quick. I know this is getting long, this 20-minute video. Okay, but let's talk about singularity, volume, and probability a little bit. Okay, so these are both singular objects. This is a point. This is supposed to be a point charge. So let's give it a little charge. Boom. I'm ground. And here, negative. Now what we're going to apply is one charge unit to each of these objects. Okay? This is a perfectly conductive, spherical, solid, could be a shell even, doesn't really matter to me. I don't think it matters to this example actually, except weirdly on the inside. But for our purposes, this has a negative charge of 1, this has a negative charge of 1. Okay, since this is a point, right, there's only one place to interact with this object. Okay, at the point of that object, this imaginary pointedness, which has no dimensions and therefore has an infinite energy density, but we'll let all that slide because, I don't know, because, okay, this is a point. So it doesn't matter where you touch the point, because there's only one place to touch a point at that point. This is very important though. This seems crazy and weird, but geometry, and it's very important. Here is a surface. Even if it was just a Planck, this is a surface. This has area. It has actually infinity times infinity number of points. If a circle has infinity number of points, then a sphere has infinity times infinity number of points. Okay, it's a whole order of surface, more points, and then we can go into the sphere too. Okay, so the thing is, this has charge of 1. Also, I touch this at that point and I ground it out. Okay, this has surface. Now, if I touch it here, that will ground it out. If I touch it here, that will ground it out. If I touch it here, it will ground it out. If I touch it here, it will ground it out. It does not matter, because this is a unity. The charge is distributed continuously over the entirety of this object. So it doesn't matter where I touch the object. But probability and stochasticism This means that I also, when this loses charge, I don't know what direction that grounding out came from, because all I know is that the charge disappeared. Or, when applying the photon model, when this photon is emitted, this is a photon propagating outwards, like this, okay, maybe we detect it here, but the photon is everywhere on that sphere simultaneously. It is a singularity, it is a unity, it is a process which is, you know, like holistic unto itself. It's not, there's not parts to this. You collapse it, you collapse the whole thing. Just a bubble, like a soap bubble, okay? It's possible, just like it's possible to cut a photon in half into a positron and an electron. You can cut a soap bubble in half, but it's a very delicate procedure. It must be done very, very carefully. When you burst a bubble, you burst the whole bubble. You don't half burst a bubble and you don't burst half a bubble. Okay? This is the whole integrated system. This is a point, and therefore it's like everything should be completely deterministic, but this means that you can't know. This is like why you can't know everything about something. As soon as you have surface, then you'd have to know where you were. It doesn't matter where you touched on the surface. It doesn't matter where that point of interaction is. The event happened. The modification happened regardless, because this is a unity. And this is a very important difference in the way of looking at the universe. To say there's a point is like saying there's nothingness. And nothingness can't exist because it doesn't exist by definition. It's nothing. There's nothing there to be. So there isn't. All of a sudden, you have a distributed thing. Doesn't matter where you interact with it. You've interacted with the entirety of the object. Very important.